Okay, so we're going to find the maximum shear at C, which is right here, and due to this set of moving loads. So the first thing I want to do is draw my influence line for shear. I'll do that right underneath it. So I want the shear at C, and for this length of the beam. And then just to help us visualize it, I'll go ahead and extend some lines down that will show us these are important points. And I want to draw the influence line on that. Now remember, for shear at C, or for shear at any point internally, I find it best to kind of imagine this shearless connector at C. Right? So the moment still is transferred, the axial force is transferred, but when I put positive shear forces on each side respectively, the Mueller-Breslau principle will help me get the shape of the structure. So looking at this left side, what's going to happen at C? Is it going to move up or down? It's going to move down. So it's probably going to pivot something like that. And then when I look at the right side piece, with the applied positive shear, is it going to move up or down? Up. So there's the shape of my influence line. Now we know that this is 2 meters and this is 6 meters. And remember, I know that this change in shear here is equal to 1. So basically it says that this height is to 2 meters as this height is to 6 meters. Well, 6 is 3 times as big as 2. So this height should be 3 times as big as that height. So I got 3 heights up here and 1 height there. That's a total of 4. So this should be 3/4 and 1/4. That make sense? Let me do it a different way. How about this? This is 2 meters and this is 6 meters. All right. I'll call this height 1 and this height 2. Okay? I know that H1 plus H2, well, the absolute values, has got to be equal to what? If I add these two numbers together, what do I get? 1. So there's one equation. My second equation is that H1 is to 2 meters as H2 is to 6 meters. So really I have 2 equations and 2 unknowns. Everybody see that? So you could solve for this. I could say, oh, H1 is 1 minus H2 and stick it in there and I'll have one equation for H1. I like to do it this way. I just like to think of it so I know that this is 3 times as big as that, so this has to be 3 times as big as that one. So I already know from this equation right here that for these things to be equal, what is it? H1, this would have to be equal to what? It would have to be 3 times H1 is H2, right? If I multiply the top and bottom by 3, I get 3H1 is equal to H2, the 6's cancel. And now I can plug that back in there and solve for it. So when I do, I'll get this is 3/4, and this is 1/4, and of course that one's negative. There's a lot of different ways to approach it. It's all based on the fact that these triangles have the same slope and that they'll be therefore similar. So since this is 3 times bigger than that, this value is 3 times bigger than that. Okay? Questions? Alright, so all I do is just, now that I have my values, I'm going to let my truckloads go from right to left and traverse this influence line. We're trying to find the maximum shear. Now just looking at this influence line, do you think the shear would be more positive or negative? it looks like since there's way more positive space or area in the influence line on the positive side than the negative side, then probably the positive shear is going to be the bigger of the two. So whenever I let these forces in turn come to the maximum value, I'm going to use 3/4, not -1/4. I'm going to always stop my load just to the right of C, try to find the largest value. So my first case, I'll call it case 1, will be when the 1 kilonewton load hits the top. So I'm going to kind of very quickly re-sketch. And you don't have to do this when you're working this in the when you're working it on the test. I'll just do it to kind of help you see it. So there's my influence line, and then I'm going to come and let the first load, the 1 kilonewton load, land at the top, and then 1 meter back is the 4 kilonewton load, and then 3 meters back is the 6 kilonewton load. And this is a distance of 1 meter and 3 meters. So that's a distance of 4 meters. What's this length here? This is 6 meters. So all the loads are on the structure. If there was a long list of these, some of them may not have been able to come onto the structure yet, so you wouldn't have to account for them all. So what I need to do now is find these values. I already know this maximum value is 3/4. What's this value and what's this value? Well, what's the slope of the line? We can do it by slope of the line, or we can do it by similar triangles, however you want to do it. The slope of the line is the rise, which is 3/4, divided by the run, which is 6. So that would be 3/24, which is 1/8. That make sense? So that means every meter I move to the right, my value drops by 1/8. So look at that. I move 1 meter, I should drop 1/8. So this is really 6/8. And I move 1 meter to the right, I drop an 8, I get 5/8. And I move 3 more meters, I drop another 3/8, so I'm down to 2/8. Any questions about that? So now with all the pieces, it's really easy to say that the shear at C for case 1 will be 1 kilonewton times 3/4 plus 4 kilonewtons times 5/8 plus 6 kilonewtons times 2/8. So somebody have to do that calculation for me. $4.75? I just guessed. So I get a positive shear of 4.75 for that case. So we just have to do it again. So case 2, I'll redraw my shear at C. There's the same influence line we had before. Now the second load hits the top of the hill at 4 kilonewtons. And then 3 meters back to the right is the last load at 6 kilonewtons. and 1 meter in the front is the 1 kilonewton load. That's 1 meter. And I'll need to know these ordinate values. Well, the slope's still the same, so again, now I move 3 meters, I'm going to drop 3/8, and I started with 6/8, so 6/8 minus 3/8 is, did I say that right? Yeah, it should be 3/8, right, 3/8, right? And what's the slope of this line? Well, they're the same slope. If you want to check, you can see that it's 1/4 divided by 2, which is the same 1/8. So I moved from minus 1/4, move 1 meter, I should drop an 8. So that's 2/8 minus an 8. This should be minus 1/8. So now the front load is actually producing a negative contribution to this particular one. So the shear at C from the second case would be 1 kilonewton times negative 1/8 plus 4 kilonewtons times 3/4 plus 6 kilonewtons times 3/8. What's that? $5.125. I'm guessing. Is it? So that's a more critical condition because you see the value is higher, even accounting for a negative contribution. Now, probably that's going to be the worst case, maybe? We'll find out. Because what happens with case 3? I don't know if I can squeeze it in here, so I may have to switch to a different sheet real quick. So the shear at C for the third case, I'll redraw the influence line. So there it is. And in the third case, now the last load comes to the top, which is the 6 kilonewton force. And then 3 meters in front is the fourth, but what? That part of the structure is only 2 meters, right? So now the first 1 kilonewton and the second 4 kilonewton force have actually left the structure on the left-hand side. So it's just one force. So in that case, for the third case, the shear at C would be the load, which is 6 kilonewtons, times the maximum value there, which is 3/4. So what's that, 4.5? So looking back, what was the maximum value? I think it was the second case, the 5.125. So now we'll say the maximum value for the shear at C is 5.215 kilonewtons, and it's positive. Any questions about that? It's a very doable problem for the exam. Questions? Yeah.
Put it up on the example on the website.
Yes, sir. So really, I think the problem for this approach has kind of 3 parts. I think 1/3 of the problem is this, and then the other 2/3 would be recognizing that you have 3 cases, and then knowing how to apply the forces at the maximum value. Make those 3 calculations and then see which one is max. Okay.